In this video, we're going to go over Hubble's law. So Hubble's law, we've probably all seen this equation, V equals hd. H stands for our Hubble's constant. So V stands for our rotational velocity, so galaxies are moving away from us, and D stands for the distance they are away. So what Hubble did is, let's say we're on Earth and we have telescopes. What he did was he observed distant galaxies or distant stars, and he saw that they are moving away from us. Remember, he only did it for stars that are moving away from us. If we go to the other side of the Earth again and we look at the stars and the galaxies over here, we can see again those stars are all moving away from us. So what he said was the speed that they are moving away from us is directly proportional to the distance they are away from the Earth. So the further away it is from us, the faster it's moving. And what he did was he did a big catalogue where he looked at the speed they're all moving away and their distance. And what he did was he catalogued all these different stars, and he found then that the gradient of that line was equal to the value of Hubble's constant. And the value used today for Hubble's constant is this number here. So 70 kilometers per second per megaparsecs. You might be thinking, how did they figure out the speed of the galaxies? And the way they figured out the rotational velocity, or the speed of the galaxies, was they looked at their redshift. So again, we said here that all of these stars and galaxies are moving away from us. If stars and galaxies are moving away from us, the light that left them has a bigger distance, a further distance to travel before it reaches us. And what's happened to the space is expanded. So that star has traveled further away from us, that light has traveled further to get before it gets to us. So the light that gets emitted gets shifted to the longer ends of the wavelength. So we call it redshift. So let's say I was looking at the spectra of a star, and we have these spectral lines inside my star. If the star gets redshifted, which means all of those wavelengths get shifted to longer wavelengths, you can see how the lines all get shifted up to a longer wavelength. So we looked at the spectra from the stars, and we can see the shift was towards the longer end of the spectrum. We're not saying the light is red, we're saying it's shifted towards the red end of the spectrum, that longer wavelength. So again, that's how you figured out the red shift of the stars. You multiply by the speed of light to figure out what their rotational velocity is, how fast they're moving away from us. And then he catalogued these speeds against their distances away to figure out what that value of Hubble constant was. So what he said was, again, that all these galaxies and stars are moving away from us. The further they are away, the faster they're moving. And you might think, how does that explain a uniform expansion in all directions? You might think, how is something further away from us moving faster? How is that uniform? And it's because the way I imagine it is to look at this. So let's imagine 1 is where us, right? That's where we are on Earth. 2, 3, 4, 5, 6, 7, 8, they're all distant galaxies, right? Let's say the distance between us and that first star galaxy is x. The distance between us and that second star galaxy is then 2 times x. The distance between us and that third star of galaxy is going to be 3 times x. So let's say space expanded. Let's say it's doubled, okay? So we're going to stay in the same place, and we're saying space is doubled. So instead of galaxy 2 or stars 2 being x away from us, it's now going to be 2x away from us. There's where 2 is. Instead of galaxy 3 being 2x away from us, it's now going to be 4x away from us. There's 1x, 2x, 3x, 4x. So there is where star 3 is now. It's going to be 2x from 2, and it's going to be 4x from 3. If I look at number 4, it was 1x, 2x, 3x away, but it's getting doubled. It's going to be 6x away. So there's 1x, 2x, 3x, 4x, 5x, 6x. So that now is where star 4 is. So we can see it's going to be 6x away. Okay? So if we look here again, remember each one represents x, so each little one represents x. This one was 1x away, got doubled, space doubled. This one that was 2x away got doubled before. And this one that was 1, 2, 3x away got doubled to 6x. 1, 2, 3, 4, 5, 6x away. So now if we look at star 2 compared to where we were, so if we compare 1 to 2, we can see it was 1x away, but now it is 2x away. So we can see that it increased by a distance of x. If we compare star 1 to, say, star 4, it was 3x away, but now we said it's going to be 6x away. So that change is 3x. So you can see again, it was a uniform expansion, all space doubled, but because of the way that it works, because of this math that we just proved, star 2 looked like it only changed by x, but star 4 looked like it changed by 3x. It went much further in distance, so that's why it went faster, right? So stars that are further away from us are going faster because they traveled a bigger distance. Okay, so that's what Hubble proved. He said that the expansion of the universe is uniform in all directions. And this is evidence then for the Big Bang theory. Because if the universe is expanding and has always been expanding, it implies that there used to be a point in time where the universe was hot and concentrated and dense in a single point. We can then use this to figure out what is the age of the universe. So, I'm just going to change colors so you can see the math. If we want to figure out what the age of the universe is, we use our Hubble's constant. So again, I have an equation here that says v is equal to h over d. I've got speed, Hubble's constant, and distance. And I know normally that speed is equal to distance divided by time. So if I rearrange this to have v over d, because of here, if I do v divided by d, that gives me Hubble's constant. So if I rearrange this to have a speed over a distance, if I have a speed divided by a distance, what we end up with is 1 over time. So we can see here that v over d, that is Hubble's constant, speed over distance, represents 1 over time. So what we have now is we're saying that Hubble's constant is 1 over time. Okay, so now I want to figure out what the age of the universe is. Time, I want to always be in my seconds, right? So if I look at Hubble's constant, it's in kilometers per second per megaparsec. So what that means is it's 70 kilometers per second per megaparsec, okay? Megaparsec and kilometers, I can't cancel those units easily to get me left with that second. That's what I want to do. So I think, how can I get rid of that megaparsec and put it into kilometers so I can cancel the kilometers in the bottom and the kilometers in the bottom? So I know that 1 parsec is 3.08 times 10 to the power 16. So instead of having 1 megaparsec in the bottom, I can write that I really have 1 times 10 to the power 6 parsecs. But I don't want to have it in parsecs, I want to cancel the kilometers, so I'm going to convert it into meters. So parsecs into meters, we multiply by 3.08 times 10 to the power 16. So now the units in the bottom is meters, but my units in my top is kilometers. So in order to cancel it, it needs to be the same, so I'm going to convert this into meters. So 70 kilometers is going to be 70,000 meters. So that's why it's 70,000 meters per second. So now we can see if I do 70,000 divided by the bottom number, we've got a meter divided by meter, and the unit we get left with is 1 over seconds, which makes sense because what that equals is 1 over time. So in our calculators, what we're going to do is 1 times 10 to the power 6 multiplied by 3.08 times 10 to the power 16. And then we're going to do 70,000 divided by that answer to get what our number is for our Hubble's constant. And mine comes out at 2.27 times 10 to the negative 18. Remember, that's a 1 over a second. That's the unit we got left with, or 1 over time. So to get what the time is in seconds, what we have to do is 1 over that value of Hubble's constant. So what we're going to do is 1 divided by your answer in your calculator to get that value of 4.4 times 10 to the power of 17 seconds. So that's the age in seconds. Again, but I might want to put that into years, right? Because that seems kind of a hard number to grasp. So to get from seconds into minutes, we're going to divide by 60. If you get from minutes into hours, we divide by 60 again. Get from hours into days, we divide by 24. And to get from days into years, divide by 365. And we get left with 1.4 times 10 to the power of 10 years. Okay? And if you Google what the age of the universe is, it comes out that the age of the universe is roughly like 13.8, 13.7, depends where you look, but roughly 14 billion years old. Okay? 14 billion is 14 times 10 to the power 9, which is roughly the same thing as 1.4. Well, it is the same thing as 1.4 times 10 to the power 10, which is exactly what we've calculated here.